Good morning, dear students, and welcome to Vista's Learning, an online educational platform. My name is Denzil, your science tutor for class 11. So let's get started with our session for today. The topic under discussion is Introduction to the chapter Measurement. This is a session 1 of the chapter Measurement. So lately we have set the bridge course for your PUC or your CBSE class 11 and class 12. So the bridge course consists of gapping the things that link between your 10th standard and your 11th standard. So we're starting off with a new chapter, which happens to be your chapter 2 in your NCERT textbook. So let us start with the first question as to what actually is a measurement. When you say you have to measure a given object or identify the dimension of a given object, what does that mean? So what are the different instruments also used in order to measure this given object? First of all, what is a measurement? Measurement is to scale a given object. Scale meaning to identify as to how long, how short, how big, how small, how massive or how small of a mass or a weight it has. So what are the different measurements of length? This session we will be discussing only one of the physical quantity under measurement, which is of length. In the following sections, we will also discuss the other physical measurement of other physical quantities such as mass and time. So here we will discuss only length. So what does it mean to measure a given object by its length? And how do you make a measurement? Why we need a measurement is clear. It's nothing but to scale a given object. So now we use a ruler to make a measurement by length. So how exactly is a ruler useful for our measurement? And how was it in the past? Now, in the past, meaning 2000 BC, the Egyptians, in order to construct the pyramids, used what is called as a cubic rod. A cubic rod is a small rod, okay, and a rod which has a certain or a standard length. Using the standard length, they were able to construct a magnificent monument, that is a pyramid. But now, after all those more of innovations and technology that it has given birth to, our sense of measurement has also changed. The measurement that we are dealing today is what we have as a standard scale called a meter scale. This scale, the ruler behind me, is what is a meter scale. So the SI unit of length is, so let me change the color to yellow. SI unit of length is meters, given by the small letter m. This 1 meter scale, which is considered to be a standard, can be cut into parts. If you take 1 meter scale and cut it into 100 parts, just like a birthday cake. When you take a birthday cake, you ask your friend to cut the birthday cake into given number of parts. It's the same thing with the pizza. A pizza is cut into certain number of slices. Now, same thing, you take a standard ruler which is of 1 meter, cut it into 100 parts. The length of one part is what is called as 1 centimeter. And remember, 100 century, centi 100. So, and that is why we call it centimeter. So 100 centimeter makes up 1 meter. The conversion between a centimeter and a meter was also discussed in the bridge course, where converting one given form to the other form, where what is the converting factor and what are the different the calculations that are used in order to convert the given into a given factor. So this is how you can turn a scale of 100 parts where one part represents 1 centimeter. So you have 100 such part which makes up total of 1 meter. Similarly, if I take the same scale and cut it into 1,000 parts, 1,000 parts, millennium, which is of 1,000, millimeter is what you call as a one part in that 1,000, as 1 millimeter. So 1,000 millimeter written by mm is equals to 1 meter. Is that all we can measure? Is that all we can break the scale into 1,000 parts? Can we break it even further? Certainly there is a way. Why, how, and why would you want to break it into more number of parts? That is because if you want to measure even in a smaller scale, an example, if you want to measure the radius of a molecule or the width of a molecule, the thickness of a molecule, then you need to use a smaller scale. You cannot use the same scale of a meter, so use a smaller scale. So what else can we do? Now, there are other different scales that you use in a meter. So I'll just mention the other scales. For example, which is 10 to the power of so let me put this as, all right. If you break the scale into 10 to the power of 6, 10 to the power of 6, yes, that would be like 1 with 6 zeros. So you break the scale into so many parts, then one part is what is called as a micrometer. Micro is given by the symbol mu. Mu is a Greek letter. All right, so let me mention it here as well. Mu is a Greek letter. Mu, M with accent, mu. This is a Greek letter to show a scale which is of a micro scale. Micro scale, microorganism. Microorganism. Why do we use microorganism? Because the scale that they exist is in the order of 10 to the power of 6 micrometer, which makes up total 1 meter. Similarly, I can go on where 10 to the power of 9 nanometers, nanoscale, nanotechnology. Today we have this nanotechnologies. That's because the technologies are dealt with a scale which is 10 to the power of 9 nanometer, which is equivalent to 1 meter, but 10 to the power of minus 9. That's like 1 by 1 with 9 zeros followed by it. That's a very small scale. Today's technology is based on a nanometer scale. So you have many more as such. So these are the basic scales that we refer to. Now there are scales even larger than a meter. We will have a look at it later. Different ranges in length. Okay, we will have a look at it later stage. So instruments that we use for this measurement. Now, different instrument. One we saw is a ruler, which we use as one of the instrument. The other instrument, in order to identify the smaller scale to a very precise and accurate value, is what is called as a screw gauge. All right, this is called a screw gauge. Screw gauge gives you a very precise and an accurate value, even the smaller values, until the magnitude of millimeters. Now you could do the same thing with a scale. You can identify what is the millimeter position on a ruler as well. So how is it different for a screw gauge? It is the order. So here's what we discuss next is the least count. The least count is the smallest value that can be measured by the measuring instrument. Smallest value. The smallest value that you can identify on your ruler. Can you tell me what will be the smallest value? If not, go ahead, grab your ruler and tell me what is the smallest value you can find on that ruler. Okay, have you got the scale with you? Now go ahead, look at your scale and tell me what is the smallest value you can find on the ruler. Now if you look close, you will see that the smallest value is about, for a ruler, is about 0. Let me not write that in centimeters, I'll write it in millimeters. Decimals, no. You do not use a lot of decimals. 1 millimeter. That is the smallest value you can find on your ruler. But some of your scale might also, if at all, might also give you which is of 0.5 millimeter. That's 1/2 of a millimeter. But for a screw gauge, it is not so. It has even smaller scale than this ruler. So for a screw gauge, the least count, I'll write it here. For a screw gauge, the least count will be 0.01 millimeter. That's smaller scale than your ruler. Therefore, this screw gauge gives you a very precise and accurate value when you're making a measurement. So where can we use a screw gauge? Is it really important? Yes, especially in construction of satellites, construction of technologies, construction of those electronic gadgets, construction of bridges as well. At times, it is necessary to use a screw gauge. Why? It gives you a precise value and accurate value. Precision and accuracy is what gives us the trust in the technologies. If there is no precision and accuracy in a technology, then you lose the confidence in using that technology because it breaks apart very easily. If you want it to be more durable and strong, yes, you need a better value by measuring. So there's also another instrument which looks similar to this one. This instrument is what is called a Vernier Caliper. Now, for those of you wondering that you've never encountered this before and it is something new, certainly it is something new that you've never encountered, but soon you will also find them in your practical lab. You will have measurement of a given object by using Vernier caliper and also screw gauge. There you will be discussing the least count of a given screw gauge and also Vernier caliper, how to identify the least count and the least count of a screw gauge and the Vernier caliper. So this is also one of an instrument, measuring instrument that is used to find the preciseness and the accuracy of a given length of an object, All right. Now we come to a larger scale. When it comes to finding the distance between the sun and the earth, can you use a ruler or a measuring tape to define the distance between the two? Or it could also be the case where you have to find the distance between two stars or distance between our closest star to earth. Now one of the closest stars that you know is sun. Yes, but other closest star apart from sun, the next closest star to earth is Proxima Centauri. This is the closest star to our solar system, and the distance is about 4.25 light years, which in terms measured in kilometers is about 4.028 to 208 10 raised to 13 kilometers. When I use this number, an exponent which is 10 raised to 13 kilometers, it means 1 with 13 such zeros followed by. Interesting, right? 1 with 13 such zeros, kilometer. Now, how were we able to determine such a big distance? Did we use a measuring tape from Earth to find the distance between our closest solar, between the star which is closest to the solar system? Did we find this a measuring tape? Certainly not. So there is a different theoretical model that we set up in order to identify this distance. This theoretical model is based on a simple activity is just by using a thumb. So here's what I want you to do. Now take your thumb, place it right in front of you. Okay. Now focus on your thumb. Place the thumb in front of you. Go ahead, try. Now focus on the thumb. Shut one eye. Focus with one eye on your thumb. Now shut the other eye. Focus on the thumb. Keep doing that. And what you notice is that your thumb shifts in the background. With the background, you notice your thumb shifts its position even though you have not moved your thumb. So this is what we call it as a parallax method. The shift of an object with respect to the background, though the object is stationary, the shift, the apparent shift in its position is what gives rise to a parallax. And how we identify the distance between the star to the earth is by using the same method, a parallax method. How is it possible? You cannot use your fingers, you cannot use your eye and then find the shift in the star's position. Rather, what happens is they make measurement at two given intervals from Earth. So let's say position of Earth in the month of June. Okay, you make an observation where the star is located in space, right? And after 6 months, Earth shifts to a new position which is opposite to the previous. June, July, August, September, October, November. Okay, so in month of November, so if those of you are wondering which month you make an observation, so June you make, July, August, September, October, November, you make another measurement so that they are in opposite position. This is like an eye. Think the two, both your one eye located at this point here, the other eye located at this point here. So when you make observation, it is like shutting your eyes. So what you notice is this shift in the star's position, which is located here. The first observation that you make, the star's position is here, let's say V. The second observation you make, the star's position is V prime. So using this method, you can identify where the star is actually located in the background. So this process, this method is what determines the distance between any planetary objects with respect to Earth, and the background for it is what is known as a parallax method. So here's a quick diagram of that distance between the two, imaginary lines that are extended towards the star. Okay, that I've put it in the form of a picture here. So let's say the star which is located at this point, subtends an angle theta with respect to Earth that is located at two different positions, at A and at B. D is the distance between Earth and the star. B is also distance between the Earth and the star. So very simple here, where AS is equals to BS, where both are equals to the same distance D. B, on the other hand, is the distance between the two intervals where the observation is made, which are directed opposite to each other. Or you could also consider the orbital diameter of Earth. So taking this into consideration, the ratio of B by D, since D would be extremely large, that's because the distance between orbital diameter is comparatively small to that of distance between the Earth and the star. That is enormous. So what happens? The ratio of B by D is very small, which almost smaller than 1. Okay, very small, very smaller than 1. And therefore, theta, the angle subtended, becomes very small. Since the angle subtended is very small, then we can set this relation where D is equals to B by theta. And this is how you can identify what is the distance from Earth to that closest star, which is Proxima Centauri. B is the orbital diameter of the Earth. Theta is the angle subtended, which can be calculated by a method called a parallax method. So this is how you can theoretically mod a theoretical model in order to identify the large scale distances between Earth and a star. If so is the case, then what about the measurement of small objects? Small objects, such as one that I have in the background. These are E. coli bacteria, which is of the order of size as 1 to 2 micrometers. So I gave you an order of micrometers. So how much is 1 micrometer in terms of a meter? We saw 1 meter is about 10 to the power of 6 micrometer, but how much is 1 micrometer? Equals to 1 micrometer, which is written in this symbol micro. 1 micrometer is equals to 1 by 1, 1, 2, 3, 4, 5, 6 of a meter. That's a lot of zeros. Then you can divide and you get 0.00. That's 1, 2, 3, 4, 5. 2, 3, 4, 5, 1 meter. So much is 1 micrometer. A very small scale even for a bacteria. We still haven't got to the molecules. We're still talking about living organisms that are in the scale of a micrometers, which is of this order. So how was this picture actually taken? Was there any such instrument? Yes. The instrument used to take this picture is an electron microscope. It's a very powerful microscope that we have today, which is an electron microscope, and these pictures were taken using this instrument. Now, a bacteria, fine. Is there anything else smaller than that? Yes, light. Light has a certain wavelength. These wavelengths also have a certain range, certain scale that we have to determine by. The scale for a light range, which is for a visible light range of the order of magnitude 4000 angstrom to 7000 angstrom. This symbol here, where you write A with a circle on the top, is an angstrom. It's a unit of measurement for light. So 1 angstrom is of the order 10 raised to minus 10 meters. Now, earlier case, we only witnessed 1 by 1 into 10 raised or 1 by 10 raised to 6, which is of a micro scale. Here we have an angstrom scale, which is 1 by 10 to the power of 10 meters. That is 1 followed by 10 zeros. Earlier, 1 followed by 6 zeros. 1 followed by 10 zeros, which means even smaller value compared to that of a micro scale. So yes, for light, it is smaller compared to those of bacteria. So bacteria are quite large in size compared to light. So even for a visible light, it is different, especially when you have different colored light. Now these different colored light are what we call as a spectrum. Each colored light has its own set of wavelength. And those wavelengths will be discussed in the next year, which is for class 12. You have the chapter called optics, so you will be learning what are the various wavelengths for different colored light and problems that are based on it. How to make a measurement, how do we make a measurement for the wavelength of light, that also will be discussed in class 12 optics. Now let us get to a practical, at least one, where we determine the molecules, the size of molecule of a oleic acid, which is of the order of 10 raised to minus 9 meters. So estimating the molecular size of oleic acid. So let's get started. So what does the experiment set up? How is an experiment set up here? So what we do is, first we take 1 centimeter cube of oleic acid and dissolve it in 20 centimeter cube of water. 1 centimeter cube of oleic acid. When I use the word centimeter cube, it means the volume. Volume of oleic acid, 1 centimeter cube, dissolved in 20 cm cube of water. Okay, easy task. Take a little bit of oleic acid, put it in water and dissolve. Next, then we take 1 centimeter cube of the solution and dilute it to 20 centimeter cube of alcohol. Oh, so I use the word water. It's not water, it's alcohol. I correct myself there. It's not water, it's alcohol. So 20 cm cube, again 1 cm cube of mixture of oleic acid and alcohol is then taken and mixed with another 20 cm cube of alcohol. So what would be the concentration of this solution? 1 cm cube of oleic acid in 20 cm cube of alcohol. Take that 1 cm cube of mixture and then diluted it in 20 cm cube of alcohol. So what will be the concentration? Well, the concentration is very simple, the amount of oleic acid. Now, this amount of oleic acid is then with some sprinkle lycopodium powder on the surface of water and a large trough as in a dish. Okay, think of a plastic plate or plastic dish, and we put 1 drop of the solution in water. So whatever mixture, the amount of water droplets that you take, we just put 1 drop of that solution in water. Then the oleic acid spreads into thin and large, roughly a circular film of a molecular thickness of water surface. Okay, so which means that 1 drop of oleic acid which you put it on water will get spread out evenly in a circular shape. Once they get spread out evenly, what happens to its thickness? Its thickness reduces. To what scale does it reduce? That is what we need to identify. By identifying to what scale it reduces is how we determine the molecular size of this oleic acid. Now, suppose we have dropped n drops in water, just like remember we extracted n drops. Whenever we drop all those n drops in water, then the volume of n drops in the solution is n times V centimeter cube, and the amount of oleic acid which in the solution, well, which is n times V 1 by 20 times 20 centimeter cube per centimeter cube. Yeah. So this is how you find the volume of n drops and also the amount of oleic acid in the solution. Finally, to determine the thickness of the film, now that the oleic acid is spread out evenly on a surface, we need to find the thickness of the film. Thickness of the film, let's say T, which is equals to volume divided by the area of oleic acid. Volume, which consists of a certain amount, where you can write it n times V by 20 times 20 times the area, which is just A. So this is how you can identify the thickness of oleic acid. By determining the thickness of oleic acid, what you do, you can find how much will be its molecular size. So that is the purpose of using this activity or this experiment, where you determine the size of a molecule. Now we enter into the next section, which is to find the various range of lengths. Now, what are the various range of lengths that exist? One, we have learned that meter can be classified into various forms as centimeter. It could also be put forth in a form of a millimeter, micrometer, nanometer. So let's quickly make note of that. So let's start with centimeter. I don't have to use that color. 1 centimeter is equals to, I hope that's visible, 10 to the power of minus 2 meter, and then you have 1 millimeter, which is 10 raised to minus 3 meters, and then you have 1 micrometer, which is order of 10 raised to minus 6 meter, 1 nanometer, 10 raised to minus 9 meter, 1 angstrom, which is of the order 10 raised to minus 10 meter, then 1 picometer, picometer, P-I-C-O, picometer of the order 10 raised to minus 12 meter, and 1 fermimeter, fermimeter of the order 10 raised to minus 15 meter. So these are the smaller scales. These are the range of small scales. Now we move to a range of higher order, big scales. So the bigger scales is 1 astronomical unit, or simply we just put it as AU. 1 astronomical unit, which is of the order roughly about 1.4 into 10 raised to minus, that's plus. Okay, 10 raised to plus 11 meters. Astronomical unit is basically the distance between the sun and the earth. How you can also calculate this distance is by using the simple trick. You know that the light takes 8 minutes to reach earth. From sun to earth, it takes about 8 minutes. The speed of light is about 3 into 10 raised to 8 meter per second. So I'll write the value here. 8 minutes. Speed of light, let's write it by c. You usually represent the speed of light with the letter c, not e. C, which is 3 into 10 raised to 8 meter per second. Find the distance by using the relation where speed of light is equals to distance traveled by time taken. So you know what is the time taken, you know what is the speed of light, so you can find what is the distance, which turns out to be approximately about 1.49 into 10 raised to 11 meters. Similarly, you have other units which is of a higher order, even a greater scale, which is light year. 1 light year. Okay, so if I'm not mistaken, 1 light year is about 9.4 into 10 raised to 15 kilometers. Yeah, 9.4 into 10 raised to 15 kilometers. That is an enormous amount. 10 raised to 15. That is 1 with 15 zeros. Wow, that's a greater scale. Now, how to identify 1 light year? The distance that light travels for 1 year. Very simple to put it across. Distance that light travels for 1 year. Remember, year is a unit again which is of time. So time taken, well, how much second is 1 year? How do you find? Well, 1 year consists of 365 days. 1 day consists of 24 hours. And 1 hour consists of 60 minutes and then 60 seconds. By multiplying this, you get total number of seconds in a given year. Also, the speed of light is a constant, which is 3 into 10 raised to 8 meter per second. Use the same formula where the speed is equals to distance by time. Time you know, speed of light you know, which is speed. Find what is the distance, and you will find it's approximately the same, which is 9.4 into 10 raised to 15. And there's just one last unit which is even greater than a light year, and this one is called parsec. So parsec, 1 parsec is 3.26 light years. That is even a greater distance than a light year. So what exactly is a parsec? Parsec is the distance, is the angle that it subtends, which is of 1 second. 1 second, you've learned that the angles are measured in degrees. Even angles can be broken down into, smaller parts. Angles being broken down into smaller parts. Now, to answer to those questions, can it really be done? How is it done? What is the converting factor? Stay tuned to Vista's Way Learning. So I will explain to you how exactly the angles are divided into more number of parts, the other parts, where you call it minute and seconds. So I hope you've enjoyed the session. Make sure you give a thumbs up, subscribe, and click on those bell notifications to further stay tuned with the classes. Do visit us at www. Visit us at www.we-learning.in to get more details about the classes that we provide. I'll see you all in the next session. In the next session, we shall discuss the topic that are related to mass. What is mass and how to identify mass? What are the standard units? So take care everyone and have a nice day. Bye bye.